Something slightly different this time. I wanted to do a quick overview of the relationships between exponential functions, and that's going to take me a long time to write, which I didn't realize at the time, versus logarithms, logarithmic functions, whatever you want to call them, because there is a relationship. They're inverses of each other. In the same way that addition is related to subtraction and multiplication is related to division, exponents are related to logarithms. So something like a times b to the x power is related to the logarithms of something. And I'm going to go over the details about what that relationship looks like. First off, let's do a couple of examples of what logarithms are. And it's good to know what exponent functions are. So that's knowledge that you need to bring with you from prior stuff that we've done. And if you remember what we've done so far, you'll remember that if I write something like 2 to the fourth power, I'll know that's 16. And that's the exponential version of an equation that I could rewrite with logarithms. And logarithms would be undoing everything we've done here. It's good to know what our parts are, so let me label these parts. The first thing you need to know is that 2 is what we call a base. Obviously, it's a base. And 4, surprise, surprise, is an exponent. Okay? And then I call it, I don't know what other people call it, but I call it a number because what the hell. Okay, so I call it base number exponent. And this is how we write this in the other way, the other format for logarithmic form. We do the logarithm of logarithm base 2 of 16 equals 4. So it's good to look and compare where our parts move to. The 2 literally came down here. Okay, so what I'd like to say is that the base is always in the bottom, base on the bottom, and that's going to be between the logarithm and the 16. And that tells me what base I'm looking at. And the question this logarithm is asking is, what exponent do I have to give this number to get this number? Okay, so again, this is the number, and the exponent that I have to give 2 to get 16 would be 4. So I have base number exponent. My handwriting is terrible, but you get the idea. So this is how we set this up. So you can see that they're inverse of each other, and they're related really heavily because of that. So let's talk about 10, because base 10 is the easiest one of these to do. If I look at base 10, and base 10 is the most obvious one for humans, because humans have 10 fingers and 10 toes, and that's where we base everything on 10 that we tend to count on, and our numerical system is based on 10. And I'm going to do a couple of values. For example, if I do 10 to the fourth power, I'll know that'll be 10,000. 10,000, yeah, okay. And then 10 to the third power is 1,000. And 10 squared is 100. And 10 to the first is equal to 10. Notice what's happening. I'm counting my zeros. So 4 will give me 4 zeros. 3 will give me 3. 2 will give me 2. 1 will give me 1. And we know that 10 to the 0 power is same thing as 1. So that's consistent with everything we've done so far. And in terms of what that means, it's good to look at what that means in the alternative form. So let me just draw a line in between the two. And I'm going to write the logarithmic version of everything here. So the logarithm base 10 of 10,000 is 4. So this 10 needs this 4 as an exponent to make that number, 10,000. Okay, so we're going to continue that down. Log base 10 of 1,000 equals 3. Log base 10 of 100 is 2. Log base 10 of 10 is 1. And log base 10 of, let me think about this, I just brain farted for a second. Yeah, 1 will be 0. Okay, so 10 to the 0 power will give me 1. So if you remember that structure, you should be okay. I'm going to change pages so you can see it again. All right, so if I have a number, okay, so I have the log base, I don't know, 5, say, of 125. You're asking what exponent does 5 need to make 125? And that answer would be 3. So logarithms are really not that bad. They're actually pretty easy. One thing you should keep in mind is that if you remember that we default things and those defaults tend to disappear. For example, if you know that 2 is a number, you know that it's got a 2 over 1 that's invisible. You also know that it may have a 2 to the first power. That would also be invisible. And you may have, what else would you have here? Oh, yeah, you may have invisible x, right? But that's 1 that defaults. And you remember that then we have square roots that defaults to 2, right? But because it defaults to 2, we don't tend to see those numbers. We don't see this, and we don't see this, and we don't see these. We just accept it as a 2, and we know that this is the square root, and we write it in that format. And the same thing with logarithms. So when I see logarithm of 1,000, what I'm saying is, because I don't see anything there, it defaults to 10. Okay, so this has got an invisible 10 sitting there that you just have to be aware of. So that answer would be 3, as we said before. But if they do give us an explicit base, then we do have to keep using that. And so the log base 4 of 64 would also be 3, because 4 to the cube is 64. Easy. I think you'll agree that's easy. Now, what else can we do with this? If we know certain rules about exponents, then we know certain rules about logarithms as well. And there are some properties of logarithms that you really want to know in order to handle the problems that are going to come up. The first one I'm going to call the power rule. The power rule of logarithms says that if I'm given a problem that looks like 10 to the x power, right, that's an exponential function, and I want to undo that, right? So that tells me that I would undo that. And remember the cat in the tree analogy we used before? I would have to take the logarithm of this, the logarithm of 10 to the x power. The power rule lets me take the x and bring it down. So the x will come down and become full size, and I'll have x log of 10. Okay, and then I need to give it a value, right? So say the x log of 10 is equal to, I don't know, 4. Okay, well, that means that I need to look at what this is and evaluate that. But remember, this is a base 10 here. Log base 10 of 10 is 1. So this whole thing travels down to 1. X times 1 equals 4. But since 1 is an identity, x is equal to 4. So I just answered the question of log base 10 to the 4th power is 4. So that does work, right? And it does make sense. This is an important rule. You want to keep that in mind. Another thing you want to keep in mind is what we call the product rule. And products, as you remember, are talked about when we do multiplication. And that's a really cool rule. And I'm going to use a calculator to show that one, because that's really a cool one. So let me bring the calculator in here. And what that says is that if I have the logarithm of a certain number, and I'm looking to simplify it. Okay, so the logarithm, say, of 32. Okay, I can break that into a couple of things if I think of multiplying. If I think of factors, I can think of 16 times 2. Or I can think of 4 times 8, right? Or I can think of, what else can 2 times, no, same thing, 8 times 4. No, I guess that's it, 32 times, well, no, doesn't matter. So that's enough, all right? And what you're going to see, if I break this into this and this, I can break this into the logarithm of their addition. So I can do the log of 16 plus the log of 2. So multiplying, addition, it's a kind of the same thing. And the same thing happens here. I can do the log of 4 plus the log of 8. The cool thing is you're going to get the same answer every time. So I'm going to do that here. Let's start with the logarithm of 32. The log of 32 is 1.505. Okay, and what that means is 10 to the 1.505 power will give me 32. I'm going to prove that remember that this most recent answer is in the memory as answer. 10 raised to the most recent thing will give me 32. Okay, and even if I rounded it off, you could get it. 10 raised to, say, 1.505. You can see 31.98. So if I added those extra decimal parts, it would go into that. So let me bring that back. What was it again? Oh, log of 32. Log of 32 will give me that. Okay, now let's do the log of 16 plus the log of 2, which is off to the side here. So I'm going to make room for it here. And I'm going to take each one at a time. The log of 16 plus the log of 2, you're going to see we're going to get 1.50. Same thing, exactly the same number. And the log of 4, don't forget to close parentheses, plus the log of 8 will give us the same value yet again. And it works every single time. It's a really, really cool rule. Okay, and that's not bad. And the reason that works is kind of like the inverse of the exponential thing, where the bases are the same. Like if you know 2 to the third times 2 squared, you would know to add the exponents. You would do 2 to the fifth. It's related to that as an inverse of this. The next one would be the inverse of that. So instead of the product rule, then we have the alternative to that, which is the quotient rule. So I'm going to write that down. Quotient rule. And that kind of tells us something similar to the product rule, but the inverse of that. The quotient rule says that if I have a number like 32 again, right, so I might as well use 32. It's worked out really well so far. Okay, I can break this up into a division problem. I can do the log of 64 divided by the log of 2, right? Or I could do the log of 128 divided by the log of 4. And that would all give me the log of 32. But if I wanted to write it this way, because it's division, it would be the log of 64 minus the log of 2. And it would also be the log of 128 minus the log of 4. And just like before, we're going to prove it. Just the example is much better to prove it. Let's do the log of 32 one more time, which you know is 1.505 something. Okay, and now we're going to do the log of 64 minus the log of 2, and we're going to get the exact same thing all over again. And I don't really have to show it at this point. You guys get the idea. 128 divided by the log of 4 will give me the same answer. Oh, what did I do? Oh, I divided, idiot. So the log of 128 minus the log of 4 will give me 1.505. So this is a really cool rule. This is the quotient rule. So to review, so far we've got the most important ones, I think, which are mega important. And the first one is a product rule. I don't know why it's down there. I'm going to bring it up. The product rule, which is that, did I say product rule? Timestamp 1227, starting at 1235. So what I've got is the first rule, which is really important, which is the product rule, the power rule, timestamp 1250. The power rule, which again says that the logarithm of any value, a raised to the power of x. Applying the power rule will let me rewrite this as x times the log of a number. I didn't prove this. I should go ahead and prove this, so let me try that one. The logarithm of, let me see, 8 to the 5th power. Okay, the logarithm of 8 to the 5th power. If I use the power rule, that'll give me 5 times the log of 8. So let's do both of those first. 8 to the 5th power, God knows what that is. Let's see. Well, 2 to the 15th power. Actually, I do know what it is, but I'm not God. 8 to the 5th power will give me this number, 4.515. But 5 times the log of 8, let me get that out of the way so you can see it. Okay, close parentheses. And we will get the exact same value. So that's the product rule. The next rule that's super important to remember is the product rule. Okay, so that's the multiplier one. And all that says, if I'm going to use general letters, that the logarithm of AB will be equal to the log of A plus the log of B. And then finally, we have the quotient rule. Well, not finally, but this is the first batch. The quotient rule will tell us something similar but different. The log of A over B will be equal to the log of A minus the log of B. Okay, so these are the most important ones to remember. I'm trying to think if there's any other ones that are really as important as this, but these are by far the biggest ones. You really want to know these. We're going to use the rules that we just learned, in particular the power rule, to solve this problem. And this one is going to be a deep dive, so you want to definitely go through this one little by little. 2 to the x plus 1 is equal to 3 to 2x plus 3. We're going to need to prove it too at the end, but let's see. The good thing about the old exams was that they used to take it in a certain form, but they may not take it like that now in Lumen. Anyway, let's get started. 2 to the x plus 1 power is equal to 3 to the 2x plus 3 power. And that means that we cannot reach this x or this x because they're exponents. So we need to use the log rule to get them down from the tree. So log is our ladder. We're going to use a log as a ladder. I get that. And now we know that the power rule will let me bring these exponents down. So x plus 1 times the log of 2 is equal to 2x plus 3 times the log of 3. And now we have a fairly easier problem, but still some complications. Let's do this one. Distributive property will tell me I have to multiply these two together. So x times log of 2 plus log of 2 will be equal to 2x log of 3 plus 3 log of 3. And we need to get x. We need to solve x. I need to bring the x's to the same side. I'm going to leave this one alone. This one's going to come over, and this one's going to leave and go over there too. So x log of 2 minus 2x log of 3 will be alone. And it's going to be 3 log of 3 minus the log of 2. And let me just thin this line down. It's a little bit too thick for my comfort. And now we're going to work with this. Now, remember how we got this x double situation to be 1 by factoring. So we're going to bring the x out. I'm going to use log of 2 minus 2 log of 3 will be equal to 3 log of 3 minus log of 2. And then this is like a coefficient situation here, so I'm just going to divide both sides. And that's going to leave me with x on one side. So I'm going to get 3 log of 3 minus log of 2 over log of 2 minus 2 log of 3. This is our answer. Now, the old exams used to take this form. And if it still takes it that way, then you're lucky. You got off easy. But just in case they don't, just in case they decide to be difficult about this, it might be a good idea to try to evaluate this and see if we can get the answer the first time out, which means we're going to need to use our calculator. This is not my calculator. Where's my calculator? Here's my calculator. All right, so let me go to that calculator, bring this bad boy in. Now, you need to be really careful when you're going to do this one because you're going to make a mistake if you're not careful. So let's go slowly. 3 times the log of 3 minus log of 2 equals. I'm just going to say equals. I'm going to divide that by the log of 2. Don't forget to open and close parentheses. Oh, I need another parentheses. I just remembered. That's going to be a double thing. I need to up 2 parentheses, so I'm going to need a second one. And I'm going to make it the log of 2 close parentheses minus 2 log of 3 close and close. I think that's going to work. And we get this number. I'm going to store that in my X so I don't have to keep looking for it. But that would be crazy. And if you're lucky, it will not ask you for this. But in case it does, then assuming that I got this right, then you're going to want to keep that number on hand and round it to a couple decimal places. So X is roughly equivalent to 1.73, negative 1.73. So negative 1.73. But because we have a calculator, you don't need to round off numbers in order to evaluate it. You can evaluate it using the full value of this. So at this time, I'm going to go back up to the original problem and put it in. Remember now that when I click the X key, I'm actually clicking that value. So the log of 2 raised to the X plus, wait, I made a mistake. Let me change that again. The logarithm of 2 raised to the, okay, X plus 1. Okay, I think that, no, something's going to not work here. I don't trust this one. I'm going to close parentheses here instead. That's not good either. Let me go back to here. Then raise parentheses here. Okay, raise that to the x plus 1. I just want to tell you, it's really dangerous. You could really make a mistake and be doing all the good things and have all good intentions and still make a mistake. So be careful with that. And I can see that I'm getting rid of my own keys. How do I get rid of that parentheses? Okay, let's do one more. No, it wants to be there. All right, well, I'm going to have to humor it, I guess. Let me insert another parenthesis up here. Maybe that'll take that. Okay, let's assume that works. Oh, it didn't work. Okay, so let me hold off. Okay, so this is what we should have. I think it'll take it. It did take it. All right, so now we're going to apply it to the other one on the other side. So what is it? Oh, wait a minute, not the log. I made a mistake. I'm going to try that one more time. 2 raised to the x plus 1 will give me this. Okay, and 3 raised to the 2x plus 3 will also give me that. That's how we know we're right. All right, so like I said, if that was complicated, it's because it is complicated, and hopefully they'll take this version in the final exam, but I just don't know yet because I'm not sure how Lumen will want to have it. I'll let you know as soon as I find out.